coming on, Arjun. It's a pleasure to introduce Arjun Krishnan from University of Rochester, and he'll be speaking today about the phase diagram of the polymer model. So please, Arjun, when you're ready.
Thanks for the invite, Sundar. This is joint work with my colleague, joint with Mkrtchyan and Scott Neville, who is an undergraduate when I was a postdoc at Utah, and now he's a graduate student in Michigan. Almost done. Okay. So what I want to do is talk about the phase diagram of the polymer model, which I'll describe in a second, but I want to start off with some standard phase diagrams in statistical physics. So the one that people are familiar with is the phase diagram for water. And I'm going to focus on the part of the phase diagram where you have water and vapor and a gas. Okay. So this is a sort of a typical thing you'd find in a statistical mechanics textbook. So this pressure here, this P here refers to pressure, and this rho here refers to density. So if you can see on the right hand side of the diagram where density is high, then we're in the liquid phase, and on the left hand side of the diagram when density is low, we are in the vapor phase, more or less. Okay. So these black lines that are drawn through the phase diagram are isotherms. Okay, so these are isotherms of constant temperature line. See, and this particular isotherm in blue is called the critical isotherm. That temperature is like 640 something Kelvin. I don't remember the exact value, maybe about 7. And so let's talk about a typical experiment and see how the phase transition happens in water. So usually you'd have some vessel, you're heating it with fire, and you'll have a piston with a fixed weight on top. Okay, so that's a constant pressure, so that keeps the pressure inside the container constant. So you'll have water here, and you'll have vapor here. Maybe I'll say liquid and gas. And as you heat this mixture, it undergoes a phase transition at constant pressure because the weight on it is constant. Okay. So on the phase diagram, this transition happens on this orange horizontal line. We start maybe with at this part of the curve where it's completely liquid. Then it hits this dashed black line. So that's called the coexistence curve. Okay, so under that curve, in that parabolic area, you have both a mixture of gas and liquid. So it hits this curve, and then slowly the liquid starts boiling off. And as you keep going to the edge of the coexistence curve, all the liquid is boiled off, and now you become just completely vapor. You can also run this constant pressure experiment so that it passes through this particular point here. And that's the critical point. It's a critical density. So it passes through the critical density, and it passes through the critical isotherm as well. There, again, you have a liquid to vapor phase transition, but it's continuous. There's no jump in the density as you go from liquid to gas, and there's no constant interface between liquid and gas, and phase transition happens all over. So there's macroscopic fluctuations and so on. You can see versions of this in phenomena like critical opalescence, but I don't want to focus on that. So the typical constant pressure phase transition that we've seen is a first order phase transition because you can see a big jump in the density, like water is much more dense than steam. And so if there's a jump in some quantity like this, it's called a first order phase transition. And this jump is usually detectable in a free energy of some kind. There's an actual jump in one of these quantities. Okay. So there are two typical free energies associated with water. The one is called the Helmholtz free energy, and the other is called the Gibbs free energy. So this Helmholtz free energy is a function of beta, which is the inverse temperature, and V, which is the volume of the container here. So this size would be the volume. And there's another sort of associated and a free energy with the system, and that's called the Gibbs free energy. And there, that's a function of beta and P. That's the pressure. And I want to note that the Helmholtz free energy depends on some extrinsic quantity like the volume, which depends on the size of the system in some sense. And this pressure is somehow intrinsic to the system. And generally, these two free energies are convex duals. I haven't made any of these things precise, but I will when I start talking about the polymer model and stuff. Any questions about that? Okay. So another typical phase transition that we see is the magnetic phase transition. So to be precise, it's the paramagnetic to ferromagnetic phase transition. And that's probably best explained using the Ising model. The Ising model has a bunch of spins in a box. So this is my box. And maybe it's on the lattice ZD or on some other graph, and there are many variants of this model, but we'll do this on a box and in Z2. So the spins are either up or down. So these spin configurations are in, say, plus or minus 1. And the Hamiltonian, or the energy of a spin configuration, is written as the sum over all nearest neighbors x and y in the box of jxy sigma x sigma y, and these jxy are positive sort of coupling constants, usually taken to be 1 or random, all Gaussian. Okay. So as you can see, the energy is low if all the spins are aligned, and but unfortunately, the number of configurations where the spins are all aligned are very low, so the low entropy states. So there's a fight between this energy and entropy in the system, and that usually drives phase transitions. Another sort of important quantity I should introduce in the context of these models is the partition function Z, which is a sum over all spin configurations of e to the minus beta times the Hamiltonian. So this is the partition function. An important statistic in this model is the overall or average magnetization. So that's written as this Gibbs average here in these curved braces. I'll write that more precisely in terms of the partition function. So that's usually written as the box sigma x, and there's a sum over spin configurations, and you have this weight or this probability, which is of the form e to the minus beta it's sigma divided by z, or Okay, so this is the net magnetization. Internal magnetic moment. So in 2D, this model is solvable. It was solved by Onsager in the 1940s, where these coupling constants are just one. There you can see the following phase transition that are represented in this graph. So there's a critical temperature, Tc, and below the critical temperature, we're in the ferromagnetic phase. So how do we detect the ferromagnetic phase? We apply an external magnetic field, and then we remove it, and then we are left with some residual magnetic moment, non-zero magnetic moment. That's aligned with the field that I applied. And once you pass Tc, you apply a magnetic field, the system will respond to this magnetic field, but once you remove it, the residual magnetic field is just zero. So it sees a phase transition from the ferro to the paramagnetic phase, but this phase transition is a continuous or second order, in this case, or kth order phase transition. It's not a first order phase transition. That's because this residual magnetic moment or internal magnetic moment, it changes continuously. It goes continuously to zero, but you can still see a jump, and that jump is its first derivative. Okay, so these are two typical phase transitions. I've noted that there are two different free energies, and I should also say that this magnetic moment is can be written in terms of the free energy as one of the derivatives of the free energy. Okay, so I should define the free energy in this case as well, just to make things clear. So typically, you'll write free energy here will be a function. So I want to introduce another parameter. So I'll write H sigma as summation sigma x sigma y, and then I'll add this external magnetic field that I'll write as H dot summation sigma x sigma box. And so again, Z will be defined as above, and the free energy is a function of two parameters, beta and H, and that is typically some limit as the box size goes to infinity of log Z. Okay. And I should note that this magnetic moment that I've defined above is dFH by at H equals 0. Okay, any questions on this so far? I went pretty quickly, but just making sure. Am I frozen? No, I think it's okay.
I think it's fine, Arjun.
Okay. Okay. As I said, we talked about these free energies. In the water case, there was a beta and there was a volume, or beta and a pressure. And in the magnetic case, there's a beta and an external magnetic field, and its dual quantity will be the internal magnetization. And we saw examples of first order, and it should not really be second order, but we just call them continuous phase transitions now. And there are all sorts of interesting questions about these phase transitions, especially at criticality. You have universal behavior, which is mostly conjectural in all the models that we consider. I should also mention that the Ising model with random coupling constants has a direct connection to zero temperature first and last passage percolation. And the polymer model is a finite temperature version of first and last passage population. This connection is through is related to the existence of bi-infinite geodesics in first and last passage population. It's due to Neville. Okay, so finally, we've arrived at the model that we're going to consider. And what I'd like to do is to sort of define analogous free energies in this model that are similar to the classical the phase diagrams that we saw for water and the ferromagnet. So the polymer model is a model of a polymer in a solution, in some solution medium like water, and has a bunch of impurities. Okay. And so the polymer is typically sort of attracted to these impurities, experiences some attraction, and it also, experiences like, collisions with water molecules. And these are typically called thermal fluctuations. In this model, the fight is between thermal fluctuations versus the presence of impurities, and one is sort of interested in the shape of these polymers in the solution, and how the presence of impurities affect the shape of the polymer. So if impurities were not present, then we would expect this diffusive behavior of the polymer because it's just experiencing collisions with the medium, and so it should look something like a random walk. And if the presence of impurities sort of really influence the shape of the polymer, then it's going to look non-diffusive because it's going to want to go, collect as many impurities as possible. It'll do something weird, and that does not look like a Brownian motion. So the classical paradigm in this model is that there is a critical temperature beta, critical inverse temperature beta, for which at low temperature the presence of the other way around. At low temperature, the presence of impurities dominate, and you have non-diffusive behavior of the polymer. And at high temperature, the thermal fluctuations dominate, and you should see diffusive or Brownian motion-like behavior. Okay. This is a known fact, and I'll describe the mathematical formulation of this phase transition in a second. Any questions so far? Okay, so the mathematical formulation of this model is due to Embry and Spencer. They said you have a field of weights. There's an x coordinate. So usually this model is described in d+1 dimensions, where the first dimension is time, and this d dimensions is space. You have paths that describe the polymer itself, and so this is a path. This model is on the lattice. So it's a lattice path. Path on lattice. So these weights are typically non-negative, and so they're attractive impurities. And so the energy of a typical path is the sum of the weights it encounters. And the partition function here is just Zn beta, where you take the expectation over some base measure on paths. Measure on paths. That's typically the simple random walk. And so to work in, so using the partition function, we can define the usual Gibbs measure, which is of the form E to the beta h of xn divided by partition function set theta. And we're interested in the behavior of the Gibbs measure on paths. We'll consider various statistical averages over this Gibbs measure, which I'll write like this. So this sum over allowable paths. And sorry, I should have another P of xn. And this is this base measure, which is going to be some kind of simple random walk measure. Not necessarily simple, but some kind of random walk on the lattice. And so to define this average, you just simply sum over all possible paths and you plug in the Gibbs measure. Okay, so how do these typical statistics behave? They were described by Embry and Spencer. So the usual statistics you'll consider here are the endpoint of the polymer under the Gibbs measure. If P is symmetric, if say it takes values in plus or minus 1 and D equals 1, then xn is more or less 0, so this is a boring statistic. And so you're typically interested in the fluctuations xn squared under the Gibbs measure, and you want to figure out the scale of these fluctuations. So Embry and Spencer conjectured that in D equals 1, we have gamma equals 2/3. So this is a KPZ fluctuation scale. And in dimension 2, they didn't say anything, but they said that gamma equals 1/2 for small beta in D bigger than or equal. This was the main contribution. And apparently this was not even expected by the physicists. And so this is the diffusive scale.
So the background disorder is you don't have to say something about that, or
you do. I just forgot to say it. That should be IID weights and with exponential moments. Or let's just say all exponential moments, so you're free to choose beta.
thanks.
The next object we need to consider in this model is this Bolthausen martingale, who noticed that basically if you take the partition function and you divide by this particular quantity m beta to the n, this is just the MGF, the moment generating function of the weights, which I'll write as e to the beta omega, maybe at the origin, and this is equal to. So I'll use this script E for expectation with respect to the weights. And previously I had written E as well. Maybe if I have some transition probability, this is expectation with respect to the base random walk. So what Bolthausen proved was that these martingales have limits just by the martingale convergence theorem. They are non-negative martingales. So Wn converges to W infinity almost surely. And he noticed using the Kolmogorov 0-1 law that either you have W infinity bigger than 0 or it converges to 0 or it's equal to 0. So this region where this martingale converges to something non-zero almost surely is called the weak disorder region. And Bolthausen showed that it holds for small enough beta, and he restricted to Bernoulli weights omega xt. It's a brilliant seminal paper. And he also showed importantly that a central limit theorem holds in, again, when this weak disorder holds. This weak, strong, and all of his theorems are about the weak disorder region. So he showed a CLT in weak disorder. He said, fix some set A in RD for D bigger than or equal to 3. And then for small enough beta, you look at the Gibbs average of the endpoint, the indicator of A of the endpoint, that converges to a Gaussian integrated over that set A. So this is just e to the minus squared over 2 divided by 2 pi with the over 2. And he also noticed the importance of this an intersection probability of a pair of independent random walks, and it's a second moment condition that I'll talk about in a second. So what the summary of the slide is that he introduces martingale, and his martingale sort of determines whether you have Gaussian fluctuations or not. And if you can show that somehow that this W infinity is bigger than 0, and he did show it for small enough beta, you have an actual central limit there. Okay. There were many improvements to this method by Song and Zhou and co-authors. And then the main new innovations came in the early part of the century in 2002 due to Carmona and Hu, where they made sort of considered the free energy for the first time in the polymer model. They considered Gaussian weights, and they showed that F beta, the free energy, which is the limit of the log partition function, you can show this limit exists, and they did it using subadditivity, the subadditive ergodic theorem, as one typically does in this model. And they showed that it's equal to beta squared over 2 when beta is small and b bigger than or equal. So that beta squared over 2, you'll notice for Gaussian weights is just the log of the moment generating. Let me see. Okay. They noticed one more thing about this free energy, which is that it has an annealed bound in general, which follows from just the Jensen inequality, that F beta is equal to log mg, the log moment generating function for small beta, and it is in general less than or equal to this log of moment generating. So there are many natural questions. Is the free energy always equal to the log moment generating function? The answer is no. And one would like to show this. So in fact, F beta being strictly smaller than, or rather, yeah, but being strictly smaller than log MGF would imply this martingale going to 0. I'll show you. That's very easy. Okay. So there are two sort of disorder regions, one characterized by the martingale, and one characterized by whether or not F beta equals the log moment generating function, or if F beta is strictly smaller than. Okay, and I'll call this high temperature, and I'll call this low temperature. I'm not really allowed to call it high temperature and low temperature at this point because I've not established a monotone phase transition, but that's my next intention. Any questions about the quantities that I've introduced?
Any questions? Okay, yeah, I don't think so, Arjun. Please go on.
Okay. So we have a one-dimensional phase diagram for the polymer model. We've shown that at small temperatures, beta naught, that I'll write a precise formula for the martingale is in the limit is strictly positive, and the free energy is equal to the log mgf. We haven't yet established anything about the strong disorder region, whether we have the martingale converges to zero or we have strict inequality in the anneal bound. That was shown in O3 by Comet, Shiga, and Yoshida. So they gave this entropy condition that showed that we do have a low temperature region and a strong disorder region. So if you have Q absolutely continuous with respect to P, the two probability measures, you can write the relative entropy HQ, maybe the other way around, HP Q is minus the integral of log dq over dp, and this quantity, this derivative is of course the Radon-Nikodym derivative. So then they showed that if H of the measure on one single weight relative to this weighted measure, you use this usual Gibbs weight on this measure, is larger than log 2d. Then this implies that F beta is strictly smaller than log beta, and W infinity equals 0. So the argument they gave goes back to Ampere in the 70s, but their paper was nearly 2000. And then this picture was completed in 06 by Comets and Yoshida in an AOP paper, who showed that there's a monotone phase transition takes place. And I'll explain what that means. Place. And I think I have this on the next page. And so they showed that there's a beta critical, one for the martingale and one for the free energy, that divides the weak and strong disorder regimes. In general, we know that beta bar C is less than or equal to beta C, and it's conjectured that they're equal. Quality conjecture. Sure. And I also want to highlight this beta naught. This beta naught has a condition. It's the largest beta such that M2 beta over M beta squared is strictly smaller than 1 over pi d of P. Okay, so I didn't highlight this earlier. I'd mentioned that Bolthausen sort of highlighted the importance of this quantity. It's basically the random walk probability of two random walks that start at 0, and you ask for the probability that they intersect with some n. And two IID copies of the walk. So more is known in D equals 1 and 2, beta is 0. So this is due to Carmona and then generalized by Comet, Shiga, and Yoshida. And for d bigger than or equal to 3, we know that beta c is strictly bigger than 0. And that just follows from the fact that you have a weak disorder region. And then if the entropy condition that I talked about on the previous slide holds, then we also know that beta c is, maybe if I put this way, beta bar is bigger than 0, beta c is less than infinite. Okay, if entropy condition. Any other questions so far? Any questions at all?
Anybody have a question?
Okay. I'll move on. So I'm not mentioning other work, but we know, I just want to talk about what happens in a strong disorder region. Those were the advancements in the early 2010s. There's the Comets and Vargas and co-authors. And we can say a lot about what happens to F beta near the phase transition equals 1. That's due to Uber 1. So just to make the picture clear, in the weak disorder region, the endpoint, like we said, from Bolthausen's theorem, and has a CLT, so it's Gaussian. But we also know what happens in the strong disorder region. We know that the polymer likes to be localized, that we know it's, there are a few quantities where it peaks around. So delta, these are localizations. Well, we know this localization phenomenon happens, but we cannot characterize it. We cannot say, how far apart these peaks are, if there's only one peak or not. So not much is known in the strong disorder region. Okay, so now finally we get to our work, which is to expand this one-dimensional phase diagram into a 2D phase diagram, like a typical statistical physics model. So to do that, we have to go to these point-to-point and point-to-line free energies that were defined by Georgi Rasulaga-Sepulainen. This is a common viewpoint in this random walk and common viewpoint in these polymer models, but I think it's the first time that it's been recognized that it's an integrable part of the phase diagram of this model. So again, we consider now a new partition function where we condition the walks, the endpoints of the walks. And one can show using the usual subadditive ergodic theorem that if you let n go to infinity, then the log partition function converges to a function that we call a point-to-point free energy. Point-to-point because we start at the origin and we end up at this point nu. I've drawn these brackets around nu just to say, I would suppose this integer. So they also defined another partition function z hat, where they added a sort of bias to the endpoint in terms of this, in the form of this parameter h, sort of biases the endpoint. They called it a tilt, but we will call it a field because of the analogy with the Ising model that I'll talk about in a second. And I'll notice that the endpoint is free. So this is called the point-to-line free energy. And importantly, I'll talk about that in a second. I want to sort of draw this analogy between the polymer model and the easing model. And to do that, I'll write a typical random walk path as in terms of its increments. So sigma 1 through sigma n, like a spin configuration in the easing model. And d equals 1, the sigma I plus or minus 1 if you have the simple random walk. Then this h dot xn term above in this free energy, this term here, is simply h dot the sum of the increments. And if you remember the easing model, that looks exactly like the overall or net magnetization. Okay. So by analogy with easing, I prefer to call this a field, an external field. So Georgi Rasulaga-Sakulainen also established the usual convex duality relation between these. See this in statistical physics, as I said earlier, Hamilton-Jacobi-Bellman equation, random walk and random environment. Their main contribution is, of course, variational formulas for the point-to-line and point-to-point polymers connected to the theory of Boosman functions and infinite geodesics that I can't talk about in this talk. Okay. So what one can notice is that this point-to-line free energy has an annealed bound where this lambda is just log of m beta, and it picks up an extra term due to the field h, and that extra term is just the log of the random walk moment generating function for one step, beta h dot x1. And so this is a generalization of the annealed bound. It's almost trivial. And similarly, you can also consider a martingale, like the Bolthausen martingale, where it picks up this extra normalization due to this random walk and the external field. This extra normalization. And since it's a martingale, one can show that Wn of h now converges to W infinity of h almost surely. And like Bolthausen did, you can similarly construct a dichotomy. You say that either W infinity is bigger than 0 almost surely, or it's equal to 0 almost surely, but now it depends on h. As soon as you see this log moment generating function on the random walk, you can ask, what is the effect of the external field? And one can see it simply changes the kernel of the underlying random walk. Kernel of underlying random walk in the following way. So I'm almost ready to state our main theorem. We've introduced the free energies, we've introduced Bolthausen martingale, we've talked about the effect of the field on changing the kernel of the underlying random walk in a very specific Gibbsian way. Okay? There should be a beta in here that I've missed, but it's not so important. Okay, so I mentioned the relative entropy of two measures when I stated the entropy condition for the existence of strong disorder. Now I need the Shannon entropy for the random walk kernel itself. That's just defined by the sum over x and zd of p of x of p of x, and this is the random walk kernel. I'll define, because of the Bolthausen style dichotomy, the set of fields in Rd such that W infinity is bigger than 0 almost surely. is now the weak disorder region, but in H. And similarly, I can define a strong disorder region in H. And it's clear that the dichotomy says these two sets are disjoint, and in fact, they form orthogonality. Okay, so here's the main theorem. What we can see is that strong and weak disorder can simultaneously coexist at fixed beta, NB bigger than or equal to 3. Okay. So it says that B bigger than or equal to 3, fixed beta bigger than 0. If this previously defined condition holds for a fixed P, like this, remember this was the return or intersection probability of a pair of the random walks, then weak beta contains a non-empty neighborhood of the origin where we know explicitly what the free energy is, the point line free energy is. It's equal to the sum of these two log moment generating functions. And we know that the Bolthausen martingale converges to something that's strictly positive. And further, and this is what we think is interesting, if this underlying kernel of the random walk has finite range, then strong beta is non-equal to 0 as well, meaning there are some fields for which we can see strong disorder. So the second part is again implied by an entropy condition. We like this formulation, which we haven't seen before. So it says, if the relative entropy of these two distributions on the weights, so this is the relative entropy, and this is bigger than the Shannon entropy of a random walk, then of the random walk biased by field H, then the strong beta is non-empty. We don't know if this entropy condition holds in general, but if P has finite range, then this entropy condition holds, and we can show there exists H such that this HQ is equal to 0, and this relative entropy is always positive. So we know there exists H for which strong beta is non-empty. Okay. So notice that both these conditions are comparing weights versus the underlying random walk. This is on the left-hand side, we have something that involves the weights. And here we have a quantity that involves a random walk. And similarly, we have an entropy that involves just the weights. And here we have an entropy that compares to the random walks. And we can sort of play off these effects against each other to show both Gaussian and non-Gaussian behavior. Okay, so what are the consequences for the endpoint? We can show that in this, if this condition holds, then we do have a CLT. It's more complicated because P is now arbitrary, so it could have covariances and so on. And so there is a CLT. You see the Gibbs measure converges to the Gaussian. So surely. So this is Gaussian in D dimensions with polynomials matrix sigma. It involves some assumptions on P. I need to assume something pretty strong. We need to assume something pretty strong, that it's sub-Gaussian in some sense, in this sense. All right, this way. But that's it. Then otherwise, the Bolthausen proof just goes through with a few extras. then the strong disorder localization is also true. We'll spend a few minutes to explain it. If you remember the Gibbs measure with some field H, I define this quantity Jn, which looks at the max of the Gibbs measure over all Z in ZD. So this was just the Gibbs measure I defined previously, but you can ignore it. And what we can show that if H is in strong beta, then the lim ins of this Cesaro average of these maxes is bigger than 0, which means along some subsequence, you do have localization. You don't show it. So in some sense, this proof doesn't have any new contributions. It's just a matter of checking that the Carmona who and how much Shiga-Yoshida method just goes through. Okay, so those were our main results. That we now have a two-dimensional phase diagram. The field can induce the phase transition, and there's some complex interplay between the temperature and the fields. We can show that the consequences we expect for the endpoint are true, that we have a central limit theorem, and for some fields and for other fields, we have localization of the endpoints where it favors some parts of the space that we. I do have a few more things to say, but let me stop and ask if I can explain anything about the results.
Any questions at this point from the audience? I guess I could ask just a quick question. Can you calculate further if you assume the disorder is of particular types?
Not in D bigger than or equal to 3. In D equals 1, if you assume that the disorder has this log gamma or inverse gamma distribution, it was introduced by Sepulveda maybe 10 years ago. Then you can compute lots of things explicitly about the free energy, but there you don't see this transition from weak to strong disorder because you don't have a weak disorder region and D equals 1, beta equals 0. More refined questions can be asked that, but maybe I won't say anything at this stage. Does that make sense?
No, that's thanks very much. Okay, maybe keep going, Arjun.
Okay, so here are the questions we'd like to answer. There are two sets of fields where you're in weak disorder and strong disorder at fixed beta. And I want to describe the boundary between these two sets. So what does that look like? Is that, some codimension one thing and in ZD, what more can you say? Is it convex or something nice? I don't know. I don't have the tools that Comets and Yoshida introduced where you have some nice monotonicity properties in beta, but once you have a field, it's much more complicated. So the interesting thing here is that as you change the field from weak to strong, then somehow the endpoint undergoes this change from Gaussian behavior to favoring endpoints. So we think that's very interesting, and there's a lot to explore there. Can we show, the analogs of monotonicity? Can we show there's no re-entrant phase transition? It appears to be true. You fix a direction for small lambda h, you can show that we're in weak disorder, and for large enough lambda, you can show that we're in strong disorder for some particular directions h. Can we show that there's a monotone phase transition? There's a region where in weak disorder, there's a region where in strong disorder. We don't know how it's yet. And the other problem is that if P is not finite range, then our method does not apply to establish strong disorder. For example, in particular, if P is Gaussian, then biasing this P with a drift doesn't really change P. It remains Gaussian. So the bigger the drift you add to a Gaussian, the more it stays the same. Okay. However, I can show. I want to notice. I want to show you some pictures. So what I'm drawing here are in blue is the point-to-line free energy. On the x-axis, I have the strength of the field H, and on the y-axis, I have the point-to-line free energy. This dotted line in green is the annealed bound. It's a log of the moment generating function. So sum of the logs of the moment generating functions of the weights and the random. So clearly you can see at around H equals 2.6, at beta equals 0.5, you have these two things separate and you have a phase transition. It's a point of non-analyticity. And for beta equals 1, you can see that the critical H goes closer and closer to 0. And so this one is at beta equals 3. It's even closer to the origin. At beta equals 5, it gets even closer to the origin and so on. We can explain this. We do have an explanation for this. And that's my final theorem. That is, we can say, if some field is in strong beta naught, then beta naught H divided by beta is in strong beta for every beta bigger than beta naught. So at larger beta, you scale that H, even smaller H's will be in strong disorder. So that we can prove using a classical technique, using the FKG inequality. Yeah, but it's cheating a little bit, and it's just some clever bookkeeping in some sense. So yeah, I'll stop there. That's all I wanted to say about this.
All right. Well, let's thank Arjun for a very nice and very interesting talk. Thanks, Arjun. Could I ask if there are any comments or questions from the audience?
Hey, so okay, yeah. So in these pictures that you showed the at this critical beta, the blue line looks like a straight line.
Past the critical beta, yes. Yes, that is very reminiscent of the phase transition in the branching random walk. So yeah, I don't know how to show it. I'd love to be able to show it. It's a great question. Yes.
Okay. And maybe another question is also sometimes if you assume that during the in the storm or on situation, just assuming that you can get more information about your partition functions, can you do something like that? Just I mean, I don't know exactly what, but sometimes, especially in percolations, you just assume that you're in the supercritical, then you can obtain more and more information about.
Meaning, if you assume you're supercritical, you can get, like exponential decay of correlations or something like that.
Yeah, something like that.
I don't. Yeah, it's a good question. Again, I don't know. I haven't thought about that.
Okay.
You can say some things in strong disorder. You can say if you assume strong disorder, then you can show that the measure is localized, on the endpoints is localized. It's definitely non-Gaussian. It likes these favored points and so on. But that's all I know in the strong disorder regime. And those things that you can show are pretty soft. I don't know if you can do the kind of things that you can do in percolation. It's an excellent thought for future research.
Then in your model, it seems that you change your environment at each time, right? So could you say something if you keep the environment once for all?
You mean at each time I resample and I have independent weights? Is that right?
Well, I understood that you do that in your model.
But can you
Don't
say more? Yeah,
Yeah.
like random walk and random environment, where it would be much more similar to random walk and random environment. If you did not have this independence in time, we would lose some of the tools like this martingale property. I don't know how to recover if we did that, and that's somehow key. The second moment method says something about the martingale to establish the space transition. If we didn't have this independence in time, yeah, I haven't thought in that direction that much, to be honest with you. So,
But would you expect a phase transition in that case? I mean that you.
I don't know. I can't say because I don't know the random walk and random environment results as well, and I'm not sure what's known or what's not known there. I'll think about it and get back to you.
Okay. Well, thanks. Thanks for the talk.
No, thanks for having me. Thanks.
Yeah. Any more questions, the audience? All right. Well, let's thank Arjun again for a very nice talk, and thanks Arjun for coming on. And let's reconvene and close the seminar today and reconvene next week. Okay. Thanks very much.
Thanks, everyone.
Yeah. Nice stuff, Arjun. So
We'll talk again soon. So.
Yeah.